Welcome back to A-Level Physics. I hope everyone had a really good Easter break. Today we are going to start our new topic, which is going to be on thermal physics. It's not really going to be much new stuff. A lot of it you'll have encountered already at GCSE, or you'll have seen in chemistry if you've taken that as one of your options for A-Level. But hopefully it will give you some insight and a good bit of background into what this module will be about. So, without further ado, let's get started. So, what we need to think about first is that we are now going to be using the Kelvin scale for temperature. Now, Kelvin scale is basically something that will deal with absolute zero. In other words, 0 Kelvin. That's around minus 273 degrees C. At 0 Kelvin, all molecules in our universe have zero kinetic energy, so everything theoretically stops. At higher temperatures, molecules will have more energy, and in fact, with the Kelvin scale, we'll see later on in this topic that a molecule's energy is proportional to its temperature. Kelvin scale is named after Lord Kelvin, who was the first person to suggest it. A change of 1 Kelvin is the same as a change in 1 degree C. So you don't have to worry about questions and conversions that will have anything to do with changing between degrees C and degrees C or Kelvin and Kelvin. What you do need to worry about is if you need to change between Kelvin or degrees C. So we'll do that by having a look at our little number line. If I draw that along here, right at the bottom, we'd have 0 Kelvin, and that's the equivalent of minus 273 degrees C. That means here, at 273 Kelvin, we'll have a temperature of 0 degrees C. Here, at a temperature of 373 Kelvin, we'd have a temperature of 100 degrees C. So to go between them, you just need to add or subtract 273. Okay, great. So next, what we need to think about is the internal energy. And in this instance, we're going to be looking at it specifically at the internal energy of a gas, although a lot of these things do also apply to liquids and solids. So, the speed distribution of particles in a gas depends on the temperature. That's something that you will be familiar with from GCSE. If the temperature increases, then we also know that the average particle speed increases. That means that the average kinetic energy of the particles will increase. And if we were to look at this on a distribution curve, we would see that we have a spread out of particles. Okay, so if we have a look at speed versus the proportion of particles with a given speed at, let's say, 200 Kelvin, we'd expect a distribution curve of something like this. Okay, so particle speed's going to go along the bottom. And our proportion of particles with a given speed is going to go up the side. And for particles at around 200k, we would see a distribution of those particles something like the following, if this is 0. Okay, so most would be within that chunk of our distribution curve. If we increase the temperature to, let's say, 500 Kelvin, so this is for 200 Kelvin, if we now do it for 500, we'd expect a more spread out distribution of particles. Something maybe like that. And that's for 500 Kelvin. If we have an unideal gas, we also need to think about particles having potential energy, which you should remember from GCSE, depends on the random and relative positions of the particles. And the combination of kinetic and potential energy can lead us to define something called the internal energy. The internal energy, and this is a good one for your glossaries, of a body is the sum of the randomly distributed kinetic and potential energies of all its particles. Now this is something at GCSE that you will have merely thought about as the thermal or the heat energy, and teachers might have thrown in that it's actually referred to as internal energy. Now you really must come to think of it as the internal energy. From this as well, we want to start thinking about thermodynamics. Now everything on this slide isn't something that you necessarily need to know for your for your A-level exam, but it is useful for you to have some insight of. And if it so happens to be one of the choices that you make, that you're taking physics at university, then you will come back to look at thermodynamics in a little bit more detail then as well. You will know that if we change the internal energy of a system through heating or doing work, then we can define what is known as the first law of thermodynamics. Here, if we think about it, our system is a volume of space filled with gas, and just like in any other systems that we have in physics, we can have them either open, i.e. we let gas flow in and out, or we'll have them closed, which does not let the gas escape. First law of thermodynamics can be written as Q is equal to delta U plus W. That's where Q is the energy transferred to the system by heating in joules. U is the increase in internal energy. And that's also measured in joules. And W is the work done by the system, also measured in joules. Q can actually be a positive or a negative value. If the energy is transferred to the system, i.e. the system gets heated, then Q is positive. But if the energy is transferred away from the system, then Q is negative and the system is cooled. Like I said, this part is actually not going to be on your specific A-level exams. I'm just showing it to you because I think it is really helpful. I also think it will be really helpful for us to have a look at an example of this too. So we're going to do that now. So let's say, for example, that we have a cylinder that's sealed by a movable piston. In that instance, it might look something like this. Okay, so there's our piston, which is our little circle with our little bit that I've just coloured in there. That can move up and down, and that's trapping our gas inside of our cylinder. If we say the gas in the cylinder is heated by 60 joules of energy in order to move the piston, and the internal energy of the gas increases by 5 joules, we can use our first law of thermodynamics to calculate the work done by the gas to move the piston. Okay, so in this instance, because we've got heat that's being input and the gas is doing work, we know that Q and W are both going to be positive. So if we have a look at our equation, Q equals delta U plus W, we know that Q and W will both be positive numbers. and we substitute in the numbers that we already know. So we've been told that the gas in the cylinder is heated by 60 joules. So that's the energy transferred. And the internal energy of the gas increases by 5 joules. We're going to end up with our equation looking like this. Therefore, work done is going to be equal to 60 minus 5, which is equal to 55 joules. So 55 joules of work is done by the gas to move the piston. Okay, pretty simple like that. Obviously, it will get a little bit more complicated. That's why you look at this mainly at university or in the engineering topic if you were going to choose that as one of your options. But that's as simple as it gets in this instance. Okay, moving away from the first law of thermodynamics, then back to what we actually need to look at right now. So we've got a little bit of a blast from the past. If we think about specific heat capacity, this will be something that you definitely did encounter at GCSE, and you need to know about again in terms of the equation and what it is for A-level. So, specific heat capacity is concerned with when we are heating a substance. Now you should remember that heat is always transferred from hotter substances to cooler substances. If we heat something, it means that the particles get more kinetic energy and the temperature of the substance will also rise. From this, we can define the specific heat capacity of a substance. It is more specifically known as the amount of energy required to raise the temperature of 1 kilogram of substance by 1 Kelvin, or 1 degree C. At GCSE, you will have thought about it all in terms of degree C. At A-level, unless specifically asked, you'll be thinking about it in terms of Kelvin. In other words, we can also define our equation as Q is equal to mc delta theta. This time we've got Q being our energy change, and it's measured in joules. M is the mass of our substance, measured in kilograms. C is the specific heat capacity, and that's measured in joules per kilogram per Kelvin. Or joules per kilogram per degree C. And theta is our temperature change. Again, that's measured in mainly Kelvin at A-level or degrees C. So let's have a look at an example. The specific heat capacity of water is 4,180 joules per kilogram per Kelvin. If 172 kilojoules of energy is supplied to 5 kilograms of water at 300 Kelvin, what will its final temperature be? So we start by writing our equation. And in this instance, we're trying to find the temperature, the change in temperature even, so that's delta theta. So we can rearrange our equation straight away to figure that out. That's going to be equal to Q over M times C. We've got numbers for all of those things, so we can just plug them in. We've got 172 kilojoules, so that's 172,000 or times 10 to the 3, which is what I'm going to put down. Multiplied by the mass, which is 5 kilograms, and the specific heat capacity, which is 4,180. Plugging that number into my calculator, I'll end up with 8.229 Kelvin. Obviously, that's my temperature change. We've been told that the water is at 300 degrees Kelvin, or 300 Kelvin, sorry, and we want to know the final temperature. Therefore, we're going to have to add what we've just found out here to 300. So our final temperature is going to be 300 plus 8.229, which is going to give us a temperature of 308.229 Kelvin, or 308 Kelvin to 3 significant figures, because that's what the question is written in. So that is my appropriate significant figures for my answer. Again, it doesn't really get much complicated than that. What you might have to think about is if you are given your specific heat capacity in Kelvin, but you're given your temperature in degrees C, in which case you're going to have to convert between Kelvin and degrees C. But that's mainly as complicated as it will become. Okay, we also need to start thinking about changes of state or change of phase, whichever one you prefer. So that's looking at the changes between solid, liquid and gas. Now, we don't need to do too much stuff on this because you will have focused on this quite a lot at GCSE, but it's always helpful to remember our heating curves, which again you will have also picked up at GCSE. So our heating curves are our graphs that look something like the following. We've got our internal energy, which we'll measure in joules, and our temperature going up the side. Then we'll have our heating curve looking something like that, and that should be ringing some bells for you. So here we have our ice or liquid water. Here we've got, so that's here, sorry. And here is where we'll see our change of state. So in any part of our graph where we see an increase in temperature, so that's here and here, we're also technically seeing an increase in kinetic energy. When a substance changes state, we don't see a change in kinetic energy, we mainly just see a change in potential energy, because obviously we're breaking the bonds between the particles or the molecules. So at the horizontal portion of our graph here, we see a change in potential energy. And that's all you really need to remember for changes of state. Keep this graph in mind because it will be really helpful. The main bits to think about are the fact that an increase in gradient means an increase in kinetic energy, and a gradient of 0 will give us a change in potential energy, because that's really what we're trying to think about here. Now, because we're thinking about changes of state, the last thing that we also want to think about for this lesson is the latent heat, or specific latent heat. That's when we have to specifically thinking about the breaking of the bonds inside particles. So in order to break bonds in a particle, we obviously need to have some kind of energy. And that energy is referred to as the latent heat. In other words, the specific latent heat of fusion, which remember is when we have a substance that is melting or freezing, or vaporization, so that's boiling or condensing, is the quantity of thermal energy needed to be gained or lost in order to change the state of 1 kilogram of substance. And we have a much more simple equation to define the specific latent heat, which is that Q is equal to M times by L. And once again, Q is our change in energy, M is our mass, and L is our latent heat. So a little bit easier in terms of using for our equation. What we really need to think about is whether or not we've got fusion or vaporization. So remember, like I've already said, fusion is when we have something that is freezing or melting, i.e. they're fusing together. Vaporization is boiling / condensing, or evaporating / condensing, however you want to think about it. So let's have a look at our final example. Find the energy needed to turn 1 kilogram of water at 90 degrees C to 1 kilogram of steam at 110 degrees C. The specific latent heat of water is 4,180 joules. Sorry, that's not the specific latent heat, that's the specific heat capacity. So the specific heat capacity of water is 4180 joules per kilogram per Kelvin, and the specific heat capacity of steam is 1,890 joules per kilogram per Kelvin. And the latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kilogram. Okay, so bit to unpack here, but relatively straightforward if we follow some simple steps. First of all, we want to find the energy needed to heat the water at 10 degrees, okay? Because that's what we need to think about first. So finding that, we're going to use our Q is equal to MC delta theta. That's going to be 1 times by 4,180 times by 10, which gives us a total of 41.8 kilojoules. So that takes us to 100 degrees, which is where water will start to boil. Then we need to find the energy that will turn the water into steam. So Q is equal to ml, which is equal to 1 times 2.26 times 10 to the 6, which is fairly straightforward and just gives you 2.26 times 10 to the 6 joules. And that's all to do with getting the water to 100 degrees, which is where it'll start to turn into steam. Then we need to also find out the energy needed to heat the steam by 10 degrees. So again, we go back to our specific heat capacity equation. So that's 1 times 1,890 times by 10, which is 18.9 kilojoules. And then to find the total energy, we're just going to add all of those numbers together. So we'll get 41.8 kilojoules plus 2,260 kilojoules. I've just converted 2.26 times 10 to the 6 to 10 to the 3 there. And then I'm plussing that to 18.9 kilojoules. And that will give me a total of 2,320.7 kilojoules, which if we put the appropriate amount of significant figures that the question is giving us, which we can see is 3 sig figs, that's going to be 2,320 kilojoules. Okay, so we found, first of all, the energy needed to turn to heat the water by 10 degrees, which is going to get to boiling point. That's what we did here. And then we found the energy needed to turn the water into steam, which is here. And then we found out how much energy was needed to heat the steam by 10 degrees, which is here. And then we're going to add them all together. So something quite simple you've had to break down into a couple of steps, but those steps are not particularly difficult if you know how to use the equations that we need here, i.e. specific heat capacity and latent heat. Okay, so that's kind of it for this first lesson. What we would normally have done at some point in between this first lesson is we would have recapped the practicals that you did at GCSE. So if you remember the practical for specific heat capacity at GCSE would be looking at the blocks of metal with a heating element put into them, small amount of water in a hole with a thermometer attached to it, and then heating it up with a simple circuit to look at specific heat capacity. At A level, we would have taken that one step further. I don't think it's a required practical, but it is a practical that you can be asked questions on in your A level exams. Now, obviously, because of the situation that we're in, we can't do this practical right now. So I would recommend that you go away and look it up. It would be finding specific heat capacity using something called a continuous flow colorimeter. So I'll write that up here for you. Okay, so a continuous flow So what I would recommend that you do now, because we've reached the end of the content that I wanted to give you for this first lesson, is go away and have a look at how you would go about measuring the specific heat capacity of something using one of these continuous flow colorimeters, and make sure that you're happy with the way that it's done. There'll be a wealth of videos that you can find online that will show you how to do that. On top of that, what I'd like you to do is find the section of your textbook that has this first little chapter in it. Now, again, I'm not entirely certain what page it is in your actual textbook because I don't have the... No, I don't think you can actually, can you? Because you don't have your A-level textbooks right now. Okay, let me figure that one out, and I will upload the questions that I'd like you to complete as an extra little Word document. Sorry about the weird ending there. So yes, I will upload the questions for you to complete alongside this PowerPoint. Next time on Wednesday's lesson, we'll start to have a look at some specific gas laws, and we'll also introduce back our knowledge retrieval, because you can watch this video as many times as you like between now and then. Like I said, if you've got any questions at all, then you can email me, and I will try and put together a big PowerPoint on all of the questions that you could potentially have asked during the week for this part. Again, if you don't have any questions, that's completely fine, but it means that you won't be getting a Friday PowerPoint to go through. So that's it. Have a go at the questions. Wednesday's lesson, we'll look at some gas laws, and I'll give you some actual exam questions to prep on as well. Take care. Email me if you need anything.